All right, some discussion of concepts from Chapter 2. This is a chapter that's full of history, and some parts of this are very difficult to write fair test questions on. They're more background than they are questions on which you can be asked to do detailed calculations. So we're going to have a tour through some of these topics gradually. Before you is the list of learning objectives for Chapter 2. This first segment will be some topics from the first one of these regarding wavelength, frequency, and energy of electromagnetic radiation. So, Chapter 2's title is Periodicity and the Electronic Structure of Atoms. This picture of a rock formation shows a periodicity in the fact that there are some repeating patterns amongst those shapes in the rocks, which is something that happens in nature from time to time. Well, let's see how that applies to atoms. If one looks for some experimental evidence, and you have to have known where to look, one can find patterns in things such as the atomic radius of elements, and if it's graphed as a function of atomic numbers, then one can see where there are rises and falls in this pattern, in this graph. There are minima for certain elements. They happen to be in the group 7A elements. And the maxima are for group 1A elements. In other words, the radii of elements has a pattern as you go from one atomic number to the next, from hydrogen to lithium. Across the first group of elements from lithium to fluorine, it goes down. From sodium to chlorine, the radius goes down. The peak is again at potassium, and then it goes down, and well, there's a few other interesting things along the way, but it ends up low at bromine and high again at rubidium. And for the remaining group 1 elements, those are each the top of a peak and in the atomic radii. By the end of the chapter, we'll come back to atomic radii, but the goal of this chapter is to make some sense of these patterns that we describe as periodic patterns. We call it a periodic table because the period starts at the left end of the chart and goes across to the right, and in particular patterns or particular properties such as the atomic radius, and this is just one example, there will be properties that change gradually as one goes from left to right across the table. Well, where does this derive from? And that's the quest of this chapter, is making some sense of that. So it has to do with electromagnetic spectrum of radiant energy and how energy makes up that spectrum. There's all kinds of forms of energy in that spectrum, and we'll look at a chart of that in a moment. And energy is characterized by 3 different things: the wavelength, the frequency, and the amplitude. Those are all just terms that actually come out of math. Perhaps you've seen that before. And you can think of waves on the shore, and you can see how they come in rows along the beach. Water running up onto the beach is similar in idea to the energy in electromagnetic waves. This chart here looks like a math exercise, or physics maybe to you, where we're looking at those different aspects. So wavelength is the distance between successive peaks of energy. The frequency is the number of wave peaks that pass a point per unit time. Each of these is given characteristic variable names. Wavelength is the Greek letter lambda. Frequency is the Greek letter nu, which looks like an italicized V, honestly. Lambda has its own thing. It doesn't really look like anything we see in our normal alphabet. And so frequency and wavelength are 2 of the characteristics we commonly are going to describe when we're discussing radiation. The other aspect of the electromagnetic energy is amplitude. In other words, how high, how much energy there is in these waves from the center. And so there are peaks and troughs in any wavelength, in any wave diagram. And so if you're looking at different colors of light in the electromagnetic spectrum, I'll show you that in a moment. Violet light has a much shorter wavelength of approximately 400 nanometers. Nanometers is 10 to the minus 9. And infrared radiation on the other end of the visible spectrum is 800 nanometers, much longer wavelength. So what we perceive as electromagnetic energy is different kinds of wavelengths and different kinds of frequencies. Some of them are visible and some of them are not. Just relative numbers for the violet and infrared, you can see that they're hundreds of nanometers. Memorizing these numbers is not really the point at the moment. The entire electromagnetic spectrum goes from very, very short wavelengths on the left of this diagram to very, very long wavelengths at the right. And so the pattern is what? The lower frequency has less energy, lower frequencies, and the higher frequencies have more energy. The higher frequencies are the shorter wavelengths. The shortest wavelengths are things like gamma rays. And X-rays are a little bit longer than that. The things with the longest wavelengths are things like radio waves and such on the other end of this. And so trying to compare these things, these are all, the frequencies are at the bottom here on that chart, and the wavelength is at the top. So 10 to the minus 12th is meters, is the shortest wavelengths here. The longest ones are in the range of a meter. Radio waves are rather long. It's kind of funny that way. So you need to get to the idea that higher frequency means more energy, and that lower frequency has less energy. Lower frequency is also longer wavelengths. All right, so those are some comparison values to look at if you need to look one up. Now, the physicists have told us, and we don't have to question this, it's fine, that the wavelength at times the frequency gives us the speed of that electromagnetic energy. So the wavelength is lambda. That funny Greek letter nu is the frequency. You multiply those together and you get the speed. And so for the electromagnetic energy, all of that is going to end up being the speed of light, that speed. Electromagnetic energy is like light in different variation, or in shorter and longer wavelengths than that. So the wavelength is in meters. The frequency is in what we call hertz, which is reciprocal seconds. 1 over a second is another name for the hertz. And then the speed of light is therefore given in meters per second. That's the common unit we're going to see for that. The one will be convenient to use. To 3 sig figs, it's 3 times 10 to the 8th meters per second. So if you wanted to use that in a calculation, what would you do? And here's one that's written out for you. We'll just kind of talk our way through it. If you're looking at light from a mercury street lamp, sometimes you've seen those. They're kind of a bluish tint to them. And they have a wavelength per se, let's say, of about 436 nanometers. Well, that's a pretty specific number. How would you determine its frequency in hertz? Hz is hertz. That's that capital H, small z. And so the wavelength is the value lambda in that previous equation. And so the frequency we want is nu, Greek letter nu. So c over lambda gives us the way to calculate the frequency. So c is the speed of light. So 3 times 10 to the 8th meters per second is on top here. And below that, you're going to put in the number of nanometers, which is the wavelength. But there's a conversion required because meters are on the top and nanometers are on the bottom. So we have to realize that 10 to the 9th nanometers is 1 meter, and that accomplishes that conversion on the bottom. Again, this becomes a math exercise. If you're paying attention to where all the parts go and punch it into your calculator carefully, you should get an answer that is reciprocal seconds. In other words, seconds to the minus 1. And 6.88 times 10 to the 14th is the value that goes in front of that. It's a calculator exercise. Be careful that you're able to do this kind of thing. It's not really hard, but the mathematics, the calculator operations sometimes get you fooled if you don't put parenthesis on exponents when they're a value in the denominator. Keep an eye. So the answer for frequency should be in the unit of hertz typically. Otherwise, seconds to the minus 1 means the same thing. All right, one example of how you can relate wavelength and frequency given the speed of light in that small equation. Now, so light comes in a variety of colors. You can separate our visible light into component colors like we see from a prism, or those that we see in a rainbow, and so you know there's red, orange, yellow, green, blue, violet. Perhaps you've heard those rainbow colors. How does that pertain to atoms? What does that have to do with all this? Well, radiant energy interacts with atoms, and the scientists back in the 1800s did far more complex things than we can fathom. And they discovered that there were line spectra, a series of discrete lines that you could find on a dark background, that were result of light emitted by excited atoms. They get the atoms excited with either electricity or heat, and light was emitted, and they figured out what they look like, and they came at different colors and different wavelengths. Different kinds of things were characteristic for different elements. So the one at the top here shown is sodium, and sodium has specific colors of light that are characteristic. Particularly a yellow one is common for sodium. Probably you've seen it in a typical flame. You see a lot of sodium color. And for hydrogen, the one the graph at the bottom, the lines in the visible spectrum are several. Some are easier to see than others, and they range from the short end down here at 410 to the top, which is blue, to the long end at 656 nanometers. These are all nanometer wavelengths of visible light, or hundreds of nanometers, and so they're unique to each element. Sodium happens to have only one in that visible range in this representation, and hydrogen has several. Where do these come from? And Balmer had done some calculations with this and tried to determine what was going on, and what things they came up with were absolutely impressive. Here's examples of what these light emissions look like. Hydrogen is on the left and neon on the right. The combination of all the wavelengths of those different line spectra gives you the reddish color for the hydrogen and the orange kinds of color for neon in what we call discharge tubes. And if anyone's ever seen the electric pickle demonstration, well, it has to do with what happens if you put electricity through the substances in a pickle. Well, there's vinegar and there's salt. So the yellow glow results from what? It's the exciting of sodium atoms, and the sodium atoms give off that yellow glow as they are heated up, and electricity is put between those two forks in this diagram in the pickle. So that's what's being happened. They give off energy in that yellow range. So what did Balmer do with this? Johann Balmer in the 1880s figured out a mathematical relationship for the 4 visible lines in the atomic line spectra for hydrogen. And he figured out there was this relationship. The reciprocal of the wavelength was equal to a constant times this relationship of 1 over 2 squared minus 1 over n squared. This little term here, relationship, gives you different values that would come out to fit the line spectrum for hydrogen. How they come up with this was beyond our present day thinking, because this is purely looking for mathematical relationships for those lines. And another scientist later named Rydberg figured out that this equation was going to fit for the entire spectrum of hydrogen, and the constant that is named R here is named for Rydberg. It's called the Rydberg constant and has a value. I wouldn't worry about memorizing it. It's kind of an interesting looking number. But as long as the values of n are greater than those for m, you can use this equation to find every line in the spectrum, the entire spectrum for hydrogen. It's related to the reciprocal of the square of the first value m minus the reciprocal of the square of the second value n. Wow. And how they did this is not for us to repeat. That's okay. This would be enough to discuss for the first 2 sections of this chapter. I will continue the recordings with section 3.